Hi students, we'll study magnetic effects of current, class 12th physics topic. So this is a part 3. I already uploaded part 1, part 2, right? So if you did not see, please go and watch that and then come back to the part 3 so that you can understand very clearly. In part 1 we discussed Biot-Savart law, Ampere's law and applications, and part 2 fully applications, how to calculate the magnetic field. So by using that laws, different combinations, right? Here also we'll do one more part now. Now here today we'll discuss one important question, even it is useful for board examinations. No, we'll calculate magnetic field, that is B due to long solid cylindrical wire. Solid cylindrical conducting wire, right? So this is one important question, no? So even for board examinations you can expect this question. Please let us discuss now. So here we'll consider one solid cylinder, solid cylindrical one part, no? This is one solid cylindrical part, here full solid cylinder, no? And in this one, no, one more condition we are going to see it, that is in this we'll see that current flowing through this one is constant or uniform. Therefore current is flowing onto this one, no? This current is distributed uniformly onto this, that means along this one, no, equally distributed onto this throughout this solid cylindrical wire. Okay, so suppose I am assuming that current flowing through this one is I, so he is having the radius is capital R. Now we will calculate the magnetic field due to this wire outside, on the wire and inside the wire. First let us take this one now, this is your axis. So at certain distance, very long distance, now we will take it now R from the center. Now we have to consider one ampere and loop, right? I am considering one ampere and loop of radius is small r, right? We can apply the Ampere's law, easily we can calculate it now. So what is Ampere's law? Integral, line integral B dot dl, it will be equal to mu naught times of your current flowing through this one now. Through this ampere and loop, how much current is flowing? Total I is the current is flowing onto this one now. So we'll take one small element here now. Therefore, so one small element I am taking now dl. So here this current is flowing. Therefore here is a magnetic field here now. So magnetic field is also dB, right? So therefore the magnetic field and this dl both are in the same direction. Cos theta, cos 0 is 1 no. So therefore you can rewrite it as integral. So B dl cos 0 so is equals to mu naught into I. Cos 0 is 1. So integral dl, so integral B is constant no, because it is at equidistance onto this. B is constant, integral dl it will be equal to mu naught into I. So B is equals to our integral of this length. The total length of this no, is nothing but circumference 2 pi into small r, it is nothing but mu naught into I. So magnetic field outside it will be equal to mu naught into I by, so this I will take it is no 2 pi into r. So this is a magnetic field due to right, a wire, a long wire, so at a distance r outside onto this one no, so we can calculate mu naught into I by 2 pi into r. So we want to calculate magnetic field on the cylindrical wire, on the surface of the wire. So you know that this radius is smaller, so therefore this radius make it as like a r. So therefore it is on the wire, you can rewrite it as mu naught into I by therefore 2 pi into capital R. So this is your magnetic field, so on the wire. And magnetic field outside the wire mu naught I by 2 pi r, it is inversely proportional to r. It is magnetic field here outside is inversely proportional to r and directly proportional to the current here, directly proportional to the current. Now this is a simple concept no, but now we will discuss what will be the magnetic field inside this one now, right? So what will be the magnetic field inside of this one now? Therefore a small distance no, we'll take it as like a small r, we can take it now. Therefore this is inside. So we want to calculate magnetic field inside of this one now, right? So how to calculate the magnetic field inside this one now, inside the small portion of this? So here small r is okay, but here total I is the current is flowing for this complete area. So from this some small amount of I dash is the current is flowing, so through this part of this. So we want to calculate I dash. So current is flowing through this small part. No, I said the current is distributed uniformly, right? So therefore now, so we want to calculate what will be the magnetic field, what will be the current in this one now. So magnetic field inside this one now we can write it as same, that is mu naught into current passing through that area by 2 pi into small r. But we want to calculate I dash here, no, I dash. So I said it is current distributed is uniform. So therefore current flowing through this area and current flowing through this area, therefore unit area, therefore current density is nothing but current by area, it will be constant. So this is a condition we are assuming now. So current density, current is flowing for this one now, I by this area, that is nothing but a pi r square. So current flowing through this one now, that is nothing but I dash. So therefore pi into small r dash square. So pi cancel here now. So therefore here I dash, it will be equal to r square by r square into I. This is your current flowing through this one now. Substitute here now. What you can rewrite it as now here. So therefore B due to inside, it will be equal to mu naught by 2 pi r into I dash is nothing but a r square by capital R square into I. So this one get cancelled out, 1 r no. So it is inside how much now, mu naught by 2 pi r square into r into I. This is your right magnetic field inside of this one. So magnetic field inside is directly proportional to R. So that means how the magnetic field is varying now. So please go through it thoroughly, try to understand here now. So here now, so from here at the center of this one now, from here as the distance is increasing, so magnetic field is directly proportional, it is increasing. But once it is coming outside, no, therefore it is falling like a inversely proportional. So how it is varying now? Very interesting graph here, no, most important this graph. So let us see here now. This is your magnetic field and this is the distance. So from the center, right, from the center, no, so it is at 0 at this point, no, then slightly it is increasing, directly proportional is a straight line. So and it comes to maximum. When it will be back maximum, no, when r is equals to r. So when it is comes outside onto this one, no, it is falling inversely proportional, no. So B is inversely proportional to R. This is B is directly proportional to R. Clear? So this graph is asked in one of your NEET examination, no. So even in board also so many times this question has come onto this, right? So please go through it thoroughly onto this. So now, right? So let us see one more concept, no. Clear? So if you do not understand, please listen one more time so that you can understand very clearly. So now we'll go for one more important concept, no. This also very important for board examination, no. So magnetic field due to long solenoid. So magnetic field due to a current carrying solenoid, right? So here also lot of things are there. What is solenoid first of all? A wire is there, no, it is in the form of like a spiral, is wound for longer length onto this, right? So I'll take it as here this is, no, so this is one wire, so it is wounded for and it is like this, right? So this long wire, right, long wire is wound in the form of like a spiral. So this is nothing but a solenoid. Clear? So this is a long solenoid. So we have to consider that this area is very smaller compared to the length of this one now. Therefore this it will be the length of the solenoid now. Clear? So here we can define it one important formula, that is n is equals to small n. Small n is nothing but a number of turns per unit length. So here we can rewrite it as number of turns, it will be equal to small n into L. Therefore here in this way you can calculate number of turns. Small n is nothing but a number of turns per unit length. So don't confuse, small n is what? Number of turns per unit length. Capital N is nothing but a number of turns. Clear? So now here there is a current is flowing, therefore this is a current, So here the current is flowing like this, and it is coming here, and it is going down, right? So like this the current will flow onto this. Like this is one circular coil, this is one circular coil, this is one circular coil, this is one circular coil. Like that, one concentric circular coils are there, therefore current is flowing. This is one circular coil, one more circular coil, one more circular coil, like that. So the magnetic field due to circular coil, it is going, and the similar way is there, therefore the magnetic field is goes on adding on to this. So therefore the magnetic field inside this one now, it will form in this way. So therefore here the magnetic field, so it is going to formed in this pattern. Based on this direction, it will be changes by changing the direction of your current onto this. Clear? Right? So therefore here, right, now, so this it will be your magnetic field, and you try to observe the magnetic field inside the solenoid. So this is the magnetic field, and this is one current carrying. So many students know, you can right, can ask the doubt, that is, what will be the magnetic field in between the gaps at the ends of this one? What will be the magnetic field? You try to observe this one. So here suppose assume that this one current is flowing inside this one. So this one current is going. Then like a cross section, try to observe. Here the current is coming like this, it's inside at this point. So the current is here, it is inside. Therefore current is flowing, it is inside. Current is flowing, it is inside. Here also it will be the same, it is outside. So current is flowing, it is outside. Here it is outside. This side it is outside. This side all the currents are inside. We want to calculate what is the magnetic field at the corners of these two current carrying conductors. So this is a current, therefore due to this one, magnetic field is inside. Due to this one, magnetic field is outward. You are understanding? So here we can rewrite it as, suppose we will take one small part of this cross section. So how the currents are flowing now? Like this. Okay, gap I took it as larger. So here this is a current, current, right, and thumb rule, current. The magnetic field at this point in between this one, what will be the magnetic field in this point now? So here the magnetic field here, due to this wire is inside, so the magnetic field due to this wire it is outward. So this gap is very very smaller, distance is smaller. Also same currents are there, inside, and downward and upward. The magnetic field in between this one is also 0. That's why in between these gaps also the magnetic field will be 0, and the magnetic field in between these gaps also magnetic field will be 0. Right? This is one of your CBSE question, so most of the times it is asked. Now there is no magnetic field outward and there is no magnetic field this side, only the magnetic field is confined to the inside the solenoid region now. So inside this one, there is a uniform magnetic field is created. Clear? So this uniform magnetic field we want to calculate it now. How to calculate now? Again we will use one Ampere law. So therefore here I am going to consider 1 Ampere loop. Here I will take one small part, one part of the concept. This is one part of our 1 Ampere loop I am going to consider it now. This is a one considered, right? So this is A, therefore this is B, this is C, this is D, right? One loop I am considering. Now we have to apply the magnetic field due to this one. No? How to do it now? Line integral B dot dl is equals to mu naught into I, right? So it is not one current carrying conductor, like that large number of current carrying conductors are there, no? So therefore number of turns into, number of currents into I. Clear? So if you do the line integral, so therefore along this I can rewrite it as, so integral, so along this line integral A to B, so B dl, right? So integral B to C, so B dl, right? Integral C to D, so B dl, plus integral D to A, B dl, it will be equal to mu naught into Ni. Clear? So now we want to calculate. See here, you try to observe, this is one line, but here the magnetic field is toward this side, and this side it will be a dl. So therefore theta is equals to 90 degree, cos 90 is 0. That means along this line is magnetic field is 0. That is BC. So along this BC is 0. So CD, there is no other magnetic field is there. Now outside is also 0. The magnetic field outside this region is 0. So it is CD, also magnetic field will be 0. And DA, therefore this side it your magnetic field, this side it will be your length onto this. Also theta is equals to 90 degree. So DA, therefore magnetic field will be 0. Now you have only magnetic field only along this direction. No? So this side it will be your DL and this side it will be your dB. The magnetic field is theta is equals to 0. So here the magnetic field is there. Here A to B, so BDL it is equals to mu naught into Ni. So now, right? So B integral DL. DL is nothing but total length. This total length is nothing but the length of the solenoid. Therefore, mu naught into Ni. That implies B into L, mu naught into number of turns into I. So B is mu naught into N by L into I. So magnetic field it will be equal to mu naught into small Ni. Clear? So here in this way the magnetic field inside the solenoid, so you can calculate it as B is equals to mu naught into Ni. This solenoid concept is very important for magnetism and matter. So we can replace the magnet by this solenoid and we can study it now. That's why so studying about this solenoid now is most important. Clear? Right? So you need to remember that magnetic field due to long solenoid is mu naught into Ni. This is where it is in the center of this one now. Right? So at the center, so it is how much now? Mu naught into Ni. N is nothing but not the number of turns. It is number of turns per unit length. This is N. Clear? Number of turns per unit length now. Clear? So small n. Keep in mind. Suppose if they are asking what will be the magnetic field at the corner, at the one of its end, so just to take this half of this one, mu naught into Ni by 2. So will be your at one of its end. Only in the midpoint, no, magnetic field will be equal to mu naught into Ni. Now, right, suppose here the medium is air, so that's why we written as like a mu naught into Ni. So mu naught is nothing but absolute permeability, right? So suppose any one medium is there inside this one now. Suppose any one some medium is present inside this one now. So therefore here some any other material is present now. So you need to calculate magnetic field. So due to that medium, it will be equal to mu into so N into I, right? So mu we can rewrite it as mu is equals to so now so here mu r into therefore mu naught, like this we can rewrite it as magnetic permeability of that medium. You have to write it now. Clear? Okay. So now we'll go for another one more concept now, similar type. So magnetic field due to toroid. This also very important. So for board examinations, no, right? Most important derivation now. Clear? So what is toroid first of all? So this solenoid is then a long solenoid. This long solenoid, what we will do now, will bend in the form of like a circular coil like this, right? So here there is a, so this is one coil is there, no? Therefore here, right? Here now we will see it now. This coil, no, we will make it like a, this solenoid is there, no? This solenoid. So it will bend in the form of like a coil. This one, no? This is called a toroid, right? So in this one, no, also there is a air is there. Even any medium is also is there. Therefore you can use mu. If it is air is there, we'll use it as mu naught. Clear? So exactly the same only, same concept again now. So suppose here the current is flowing here, current is flowing here I. So current will be flowing in this one, no, in this part. So the current will be coming out after this. And also very important, no, even in solenoid and even in toroid, no, therefore there is no connectivity between the two coils onto this. Therefore the conductivity should not be there, so that the current will be jump from one coil to another coil very easily. Therefore in between these two coils, no, therefore it should not have any contact. Therefore, so be careful, no. If it is contact is there, suppose contact is there, instead of flowing this, no, current will be direct, it will be able to flow. At that point, the magnetic field will not be proper, no, right. So this also should be very, very important, no, right. So that's why you know that in our motors and all this one, no, this coil or this copper wire is there, no, therefore there will be a one enamel will be coated onto this one, no, even though there is a contact, there is a one small enamel will be there on the wire, so that it will not make like a conductivity connectivity, right. So now there will be based on this direction, no, therefore the magnetic field will be generated. As we know, we saw this one, no, the magnetic field will be confined to this region only. Therefore, how this magnetic field is there, no, it will be in the form of like a circles, no, concentric circles here, no, right, clear. So this is your magnetic field here, no, right. So based on this direction, no, therefore here, so the magnetic field is inside of this, no, like this. So the magnetic field is confined to this region, no, like this. So current magnetic field will be flowing in this region, right. So here also the magnetic field will be 0. And outside also magnetic field will be 0, but only the magnetic field will be there inside this region, no. So we will take an average distance, average radius of this one, no. Average radius is, suppose let us take that is like a r. So you can rewrite it as magnetic field inside, therefore mu naught into Ni. What is N is now? N is nothing but a number of turns per unit length. Here what is the length of this one now? Average distance is r. So N therefore by 2 pi r. Exactly, you can consider one more region here now, like that Ampere and law we can use it. So then you can calculate it as mu naught, N value is how much now? So number of turns per unit length, that is nothing but a 2 pi r into I. So this is your magnetic field due to solenoid, clear. So inside of this one now solenoid is 0, outside is also 0, only magnetic field will be confined to this region now. Suppose if they are average, this value is not given, no. So if they give, so this is inner radius is r1 and outer radius is suppose r2, it is given, no. So you can rewrite it as capital R, it will be equal to r1 plus r2 by 2. The average of these two distance, no, you have to take it, you will get the radius of this one, no. And also here mu naught we are writing, no, because of due to this air medium is present here, no, mu naught we are writing. Suppose if it is any medium is present inside this one, no, so therefore mu into Ni we have to write it now. You understand, no? Clear? Right? So in this way we can calculate the magnetic field due to toroid now. Okay, students. So thank you. Right? So one more part we will be there, part 4. So we will do magnetic effects of current of part 4. So stay tuned to my channel now. Okay, thank you. Thank you, students.